All right, so we are going to talk today about covalent bonds and how to draw molecules that use covalent bonds. But before we do that, I'm going to talk to you a little bit about just bonding in general and chemical stability. So, in general, the more stable atoms are less likely to react. So that means anything with 8 valence electrons. I'm hoping you guys remember that those would include the noble gases that are in group 18 all the way on the far right on the periodic table. Those all have 8 valence electrons and are stable, meaning they don't want to bond, they're not going to react. The same is true for anything, or the opposite is true rather, for anything else on the periodic table because they're somewhere between 1 and 7 valence electrons. They're more likely to react. So this kind of boils down to what we call the octet rule in science. I'm hoping you recognize the prefix oct, meaning 8, from your prefix and suffix list that you guys are studying. That just means that every atom wants to achieve a stable number of valence electrons. So that's the whole point of bonding in general. Now, I do call this more of a guideline rather than a rule because it does not work 100% of the time for every element on the periodic table. Actually, there's only about 7 that follow the octet rule 100% of the time. So we'll go into that a little bit more later. So moving on to chemical bonds in general. We know that all chemical bonds have some sort of an attraction force that holds atoms together. So the transfer of electrons and the attraction force that comes from the positive and negative ions that are being formed from transferring their electrons are in ionic bonds. We talked about those last week. Sharing electrons are how atoms that are covalently bonded react together. So we're going to talk about that one today here in class. There are a few, more than a few, of you that seem to be struggling with chemical formulas. So I just wanted to throw this slide in there for you guys to review. But any sort of chemical formula can have 2 different numbers and then of course the chemical symbols. So first number is the subscript. That's what you see most often. Here our subscript is the 2 next to the hydrogen. That just tells you that it has 2 atoms of hydrogen in 1 molecule of water. One thing to note with a subscript, if you don't have a number there, like this oxygen that has no number, then we are assuming that that means that we have 1 oxygen. So we don't use the number 1, we just assume that 1 is there. Same thing with a coefficient. Those are the big numbers out front of the chemical formulas. So in this case, it would be that 3. That's just telling you that you have 3 molecules of water for this example. Moving on, we have chemical bonding. We already know that on the periodic table, we have 118 elements, but we also know that there are way more than 118 different types of matter. The reason for this is because of all of the different combinations that can occur between the elements on the periodic table to form different compounds when they're bonded in different ways. So specifically kind of honing in on covalent bonds here, we know that our definitions, just like our ionic bond definition, has 2 different parts to it. So first of all, it is a non-metal. So all non-metals, if it's bonded to another non-metal, it's bonded with a covalent bond. Those covalent bonds also are sharing their electrons. We kind of insinuated that a little earlier. So 2 parts to your definition. They're nonmetals that are sharing their electrons. The attraction force that's actually holding these atoms together is a little bit different than ionic bonds because we don't have differently charged or oppositely charged ions here. So now we have 2 neutral atoms and we have to figure out what keeps them together. So if you look at the picture that I have down below, you can see the 2 atoms. In the middle are the 2 positive nuclei, so where the protons are, and on the outer edge, in between the 2, are your 2 electrons. Those are your red negative signs here. Those 2 electrons don't typically like each other. They're both negatively charged. They don't want to hang out next to each other. But because they are both being attracted and pulled in opposite directions by the 2 different nuclei, that's what holds those atoms together. So it's the attraction between the different nuclei and the shared electrons that kind of creates a tug of war between the atoms and holds that bond together. Thinking about, if you go to your next slide, you can see this here. We're skipping this part, but where you see covalent versus ionic, which one's stronger, we know it's ionic bonds because if we go back up to our picture, if we go back up to this picture, you guys can see the attraction force for a covalent bond. The ionic bond is just a positive and a negative anions clicking together, and those are solely attracted. Whereas the covalent bonds, like we just said, have the electrons hanging around next to each other, and they don't really like each other. So it's kind of that love-hate relationship for a covalent bond, whereas there's just an attraction force in an ionic bond. Skipping down to the last two sections on your note sheet, you have some rules that we're going to go over. I'm going to read through these rules, and then we're going to do a few examples with them. So first one is that you only use valence electrons when bonding. And this doesn't matter whether it's covalent or ionic bond, because we don't care about those inner electrons. We only care about the ones on the outer edge, due to the fact that when you have two atoms come next to each other, close enough to bond, it's only those outer electrons that interact with each other. This second rule here is only for covalent bonds, and that is that each bond has two electrons in it. So when we draw a bond between two atoms, it represents two electrons. The third one and the fourth one are both have to do with both covalent and ionic bonds. So of course we already know elements want to have a stable number of electrons. Typically that number is 8. But we can also not use more electrons than what the elements already have according to their location on the periodic table and the patterns within that. Meaning you can't add another electron or even take away an electron just because that's what you need to fill your diagram. The last rule that you need to know is probably the one that the students get confused the most with, so be careful with this one. This rule, it's called honk 1, 2, 3, 4. So the H can represent either hydrogen or a halogen. So remember that your halogens are group number 17 on the periodic table. That's right next to the noble gases. But your honk rule tells you the number of bonds that an element or an atom needs to be stable. So hydrogen or any of the halogens want 1 bond, oxygen wants 2, nitrogen wants 3, and carbon wants 4. Now, oxygen, nitrogen, and carbon, that's not just those 3 atoms. That's oxygen and everything below it, nitrogen and everything below it, and carbon and everything below it. The reason is because of their number of valence electrons. So if you take oxygen, for example, or any element in oxygen's family like sulfur, they all have 6 valence electrons, meaning they need 2 more to be stable to get to their number of 8. So that's where that 2 comes in. That's why it needs 2 more bonds, because it needs 2 more electrons to be stable. The last step, or the last section of your note sheet, is the Lewis diagram steps. There are 6 steps here. The first 4 are actual steps. The last 2 are just kind of notes that I want you to have. So the first one is to use the honk rule to determine your central atom. So the atom in your formula that wants the most number of bonds is going to go in the middle. Once you have that in the middle and your other atoms around it, you can draw your valence electrons and go on to step 2. So that's where you're actually drawing your dots on each of your atoms. Then step 3 is to connect your unpaired electrons with bonds or with sticks, and I'll show you an example of this. The last step that you're going to do every single time is to make sure that each atom has a stable number of electrons. Now, there are some exceptions to that 8 rule. So we know 8 is the typical stable number. However, hydrogen only needs 2 electrons because it only has 1 energy level, so it's full with 2 electrons. Anything in the third period or third row of the periodic table and below is a big enough atom that it can hold more than 8 electrons. It's not happy about it, but it's capable if it needs to. So those are just 2 exceptions to the octet rule that I want you to know. The last 2 steps for your Lewis diagrams are, like I said, more like notes. So step 5 tells you that double and triple bonds are okay, and 1 or 2 of our examples have some double bonds in there for you to see. And then step 6 tells you that you can have rings, but you can't have triangles and squares. So what that basically means is you can have atoms put together in kind of a circle form, but it has to be at least 5 atoms or more, because you can't form a triangle with 3 atoms because those bond angles don't actually exist. The last thing that I want you to know from this slide is, again, a note, but it is probably the most important, and that is that you do not use any arrows when you're connecting atoms with covalent bonds. And that's because we're not transferring electrons anymore. We're sharing them. So we're going to use sticks to do that. So if you go to some examples here, you can do these on the back side of your note sheet or on a separate sheet of paper, whichever is better for you. But our first example, PF2H, if you look at your Hunk rule, phosphorus is in nitrogen's family on the periodic table. So it's going to follow that general trend. So it wants 3 bonds. Fluorine and hydrogen are both under the H in the Hunk rule because fluorine is a halogen and of course hydrogen is starting with letter H. So with that being said, our phosphorus is going to go in the middle with its 5 valence electrons because it's in group 15. Once you have it listed with 5 valence electrons, then the other things can just go surrounding it wherever you want them to be. So I'm going to put my fluorines here, and then my hydrogen is going to go over here. The last thing is to make sure that I have my valence electrons. So I'm going to do those in green so you can kind of tell the difference between them. Once I have those done, that was kind of rough. Then I can move on to my step 3 of my drawing Lewis diagrams, and that's where I actually connect my unpaired electrons with bonds. Now it's important to make sure that your unpaired electrons actually get connected so it doesn't look like you have an extra electron sitting over there. The last step is to count your number of valence electrons and make sure everything is stable. So if we're looking at our hydrogen has 1 bond around it, which is 2 electrons, and it is stable with 2 electrons. So we're going to leave that one alone. Looking at our phosphorus now, in the middle, we have 6 electrons from the 3 different bonds that go to the other atoms, and then 2 electrons that are only on phosphorus, not bonding. So that one has 8 valence electrons, which makes it stable. The last 2 atoms here are the fluorines. Those are both the same, so I'm just going to look at one of them. If I look at this bottom one, that's not quite as messy. I have 6 electrons only on the fluorine, and then 1 bond being paired between the fluorine and the phosphorus, so that totals up to 8. So that molecule is stable, it is happy, so it gets a smiley face. Moving on to the second example. This one is pretty difficult, but I wanted to show you a difficult example. This has carbon, hydrogen, and oxygen in it. So if we look at our Hunk rule, carbon wants 4 valent, or sorry, not 4. It wants 4 bonds, hydrogen wants 1 bond, and oxygen wants 2 bonds. So carbon's going to go in the middle, and we're going to put our carbons in a line. That's my rule of thumb, is you always start with your carbons in a big line if you have lots of them, and then if the line doesn't work, then you can try to make a circle with them, but that's only if it doesn't work this way first. So I'm going to put my carbons in a row, and then I have my valence electrons on it. Then I can add my oxygen next because it's the one that wants the next most number of bonds, again with its oxygens on it, or with its electrons on it. Then the last thing I'm going to do is add in all of my hydrogens. So those can go pretty much wherever you want them to. I'm going to put them here. You can put them wherever you want. We can always move them if needed. And then, of course, hydrogen only has the 1 valence electron that you're going to draw on each of those. Then you can go ahead and actually connect your dots. I'm going to connect with yellow so you can actually see them. So I'm going to connect my oxygen and my carbon. I'm going to connect all of my other, this is just 1 bond here, it's just really thick. So connect all my carbons together, and then I can also connect all of my hydrogens to the carbons that they're next to. Then you guys can see that I have 4 valence electrons left, but I don't have any more atoms to connect to those 4 valence electrons. So with that being said, then you can start making your double or your triple bonds. So I'm going to connect this one to the oxygen over here, so that's one bond, and then I'm going to connect this one to my other carbon, so that's another bond. So you guys can see here that the oxygen is double bonded to a carbon, which is then double bonded to a third or a second carbon. Those are okay according to step 5 on our diagrams. You need to make sure that everything is stable here. So if we look at all of our hydrogens, they have one bond, which is 2 electrons. Those are good. Each of our 3 carbons have 4 bonds around it, meaning 2 bonds or 2 electrons in each bond, so that's 8 electrons. Each of our carbons is also happy. And then lastly, our oxygen has 2 bonds and 4 electrons only on the oxygen, and so that also has 8 electrons, which makes everything happy there. The last diagram that I'm going to draw with you shows you one more thing with the formulas that might help you when you're drawing Lewis diagrams. So you have CH3OH. Again, we're going to use these same numbers from over here on our second example from our hunk rule. So we know carbon is going to go in the middle, and in this case we only have 1. So I'm just going to draw 1 with its 4 valence electrons on it. Then I have 5 more atoms here. So I have 3 hydrogens here, 1 oxygen, and another hydrogen. Typically, we don't have hydrogen listed twice. As you can see from over here, we just lumped them all together and said that there were 4 of them. But what this is telling you with the OH group here, it tells you that your last hydrogen is actually connected to this oxygen, which is then connected to the center atom of carbon. So the OH group is kind of off by itself. So with that, I'm going to draw my oxygen first, and then I'm going to draw my hydrogen next to it, because I know that those have to be connected. Then I can draw my other 3 hydrogens around my carbon. So I'm going to draw those over here in red, so you can see that those are different than the first one that I drew. Regardless, all of my hydrogens can only have 1 valence electron, so I'm going to add those in. Then I can go ahead and connect my electrons. So I'm going to connect my carbon to my oxygen, and I know that my hydrogen has to be connected to my oxygen. So I'm going to start with that first. Then I can connect all of my other hydrogens to my carbon. If you take a look, I don't have anything that's left unpaired, so I should be safe. But just to double check, all of my hydrogens only have 1 bond, so those have 2 valence electrons. Those are happy. My carbon has 4 bonds surrounding it, so that is 8 valence electrons. That is also happy. My oxygen has 2 bonds and 2 lone pairs or 4 electrons only on it, so that is also 8 valence electrons around that, meaning that is a happy, stable molecule. There are a few more examples down here using the hunk rule, so you guys can see that nitrogen always has 3 bonds, oxygen always has 2 bonds, and carbon always has 4 bonds. Hydrogen only has 1. But these are just a few more examples for you guys. If you have any questions over any of this material that is covered, please do not hesitate to come ask us. We are more than willing to help you guys if you so need it. I hope this helped or review and or go over covalent